It's easiest to make the adjustment if we make a mark on the edge of the spindle so that we can see how much it's turned and we can count our turns more easily. It's going to be much easier to do that, especially for making a bunch of very small adjustments. And we have to pay attention to how many turns we've made. So again, a lot of manufacturers recommend only a quarter turn at a time. And so if we make a mark that goes up the stem and that lines up around the edge, now I'll have a really good idea how many turns I've had. Very simply, when I turn it clockwise, that turns the spindle in and compresses the spring. So you can see that's about a quarter turn right there. That's going to allow less refrigerant to enter the evaporator coil, which is going to result in higher superheat. If I adjust it the other direction, now that's about a quarter turn the other way. Now that is going to result in lower superheat because I'm allowing more refrigerant into the valve. Again, when I loosen it, so I go lefty-loosey or counterclockwise, that's going to result in less closing force and therefore more refrigerant to flow through the evaporator coil.
All right, in this video, we're going to talk about how and why to adjust a TXV, TX valve, or TEV. And the trick here is that those are all three the exact same thing. It just stands for thermostatic expansion valve. And thermostatic means that the pressure changes with temperature. That's really all that means. So thermostatic expansion valve means that it is a valve that changes with temperature, or a balance between pressures and temperatures. And we'll talk a little bit about how that happens. Now, this is not a video on everything to do with TXVs. This is specifically how and why to adjust, but I do want to touch on a few components of the TXV. The first thing is you almost never need to adjust a TXV, almost never, unless you're working in like commercial grocery refrigeration and you're adjusting it in a case or something like that, preventing floodback and then dialing it in later on. Those are areas where you might want to or might need to adjust a TXV, but for air conditioning applications and small refrigeration applications, it's very rare that you will have to do this. But sometimes you'll find yourself in a position where someone else has adjusted a TXV, TEV, TX valve, whatever you want to call it, and you need to get it set back in. And so that would be an application where it would be quite practical. But in general, out of the box, they're going to be set the way the manufacturer wants them to be set, and issues that occur with the setting are actually due to another problem. So first, let's talk about the three forces, the three primary forces that affect a thermostatic expansion valve and what they are. And the first is the pressure of the bulb. Now, the bulb attaches to the top of the TXV, and that top portion can sometimes be replaced or serviced, and that is called the power head, and that has a charge, and then it affects the movement of a diaphragm within that valve, which opens and closes the valve. But the bulb senses the temperature of the suction line at the outlet of the evaporator coil. So at the end of the evaporator coil, that bulb is attached to that suction line and it senses the temperature. As the temperature of that suction line goes up, the pressure in the bulb goes up, and that exerts an opening force. So that TXV bulb exerts an opening force on the valve, which then causes the superheat to decrease. A lot of ideas here that I can't cover completely, but superheat basically tells us how much liquid refrigerant is feeding through that evaporator coil. And are we fully feeding it or are we underfeeding it? Fully feeding it is what we would call properly fed. Overfed would be when we have superheat that is too low or even zero superheat, and underfed would be high superheat. And we would also call that starving the evaporator coil. So when that valve doesn't allow enough refrigerant through, it underfeeds or starves, resulting in high superheat. If that valve allows too much through, that's what we call overfeeding, and that results in low superheat. So that valve helps to affect that, and the number one force to help set in that superheat at the outlet of the evaporator coil is the bulb, and the bulb is the opening force. The hotter the bulb gets, the more the valve opens. The lower the temperature of the bulb, the more the valve closes. But there are two other forces that balance against that bulb. One is the internal or external equalizer. Most of the valves that you work on will be externally equalized, especially if the evaporator coil has a distributor, so some other type of pressure drop in the coil. And the reason that is because in order to set the superheat, the valve needs to know what the pressure is in the evaporator coil, and specifically at the end of the evaporator coil. And when there's a lot of pressure drop between the inlet and the outlet, especially when there's a distributor, you have to have that external equalizer to measure the pressure at the outlet. So that is a closing force. Your external equalizer or your internal equalizer, those express themselves as a closing force that balance up against that bulb force. So you have the pressure on one side of the evaporator, you have the temperature of the suction line on the other side, and then what goes along with that external equalizer force is the spring pressure. And the spring pressure is the part that is either factory set in the case of a non-adjustable valve, but we're talking about an adjustable valve. So in the case of an adjustable valve, we can either compress or decompress that spring in order to exert either more closing force or less closing force to assist that external equalizer or internal equalizer. So a common term people get confused, they think external equalizer, internal equalizer has something to do with equalizing on the off cycle. It does not. It is the equalizing force that balances against the bulb force in order to set in your superheat. So from a very practical standpoint, how you set superheat on a valve is when you turn that spindle clockwise, that compresses the spring more, which exerts a greater closing force, which means you will have higher superheat. When you decompress that spring by turning it counterclockwise, that means that you have less closing force to assist that internal or external equalizer, and that results in lower superheat, meaning more feeding of the evaporator coil. Remember, lower superheat means you're feeding more refrigerant into the evaporator coil. Higher superheat means you're feeding less. So now I want to show you kind of start to finish how you can adjust the valve. Again, before I do that, I need to state that every valve is a little different. There are a lot of rules of thumb about how many turns to kind of get to center point and all that. You have to know your particular valve. And so you're going to want to look at the manufacturer's literature for the valve that you're working with in order to know exactly how many turns. But I'm going to show you just the basic concepts of how to adjust the valve.
All right, so I want to show you quickly what a TXV looks like. And again, some people call it a TXV, some call it a TEV, some call it a TX valve, but it's actually a thermostatic expansion valve. Some of the best resources out there on TXVs are Parker Sporlin is a great resource, Danfoss is a great resource, Emerson is a great resource. This valve in particular that I'm going to show you is an adjustable valve, so this is the one that I'm going to be showing you today. So in this kit, we've got a couple things. We've got insulation for insulating the bulb, which is a pretty important thing to do. That this bulb needs to sense the temperature of the suction line at the outlet of the evaporator coil. So if it's just kind of dangling in the airstream or it's not well attached or well insulated, then it can be affected by the air temperature, which is almost always going to be higher than the temperature of the suction line itself. So here we have the bulb, and the bulb is what attaches to the suction line, and it exerts an opening force. So the hotter the bulb gets, the more it drives the valve open, and that's in balance with the external equalizer. And again, some valves are going to be internally equalized, and those will generally be valves that do not have a refrigerant distributor that acts as another restriction point or pressure drop point. You're very commonly going to see these external equalizers, and this will attach to the suction line at the end of the evaporator coil and measure the pressure inside, and this will measure the temperature. And then the spring, which is adjusted by adjusting this stem, is what makes the difference to adjust the superheat. And again, we really want to see that superheat be between 6 and 12 in most cases at the outlet of the evaporator coil. But before we do any adjustments, we have to make sure that everything else is correct in the system, that we have a full line of liquid entering the valve. You can see here we have our inlet arrow here. So we need to make sure we have a full line of liquid coming in. We make sure of that by either measuring subcooling, making sure that's at factory levels, definitely above 0. If it's a refrigeration unit where you're in a parallel situation, then often you're going to use a site class to confirm that.
For a TXV to work properly, it has to have a full line of liquid feeding it. Now in air conditioning, we test that with subcooling. That's the standard way. So whatever the manufacturer's subcooling is, make sure you have that before you start fiddling with superheats on a TXV. In the case of built-up systems or refrigeration systems with parallel evaporator coils or cases, in that case, you're not going to be checking subcooling in the same way. So there, you want to make sure that you have a full site glass. In refrigeration, they'll refer to that as a full site glass. But the result of proper subcooling or a full sight glass is a full line of liquid. So you have to provide that valve with a full line of liquid.
Now this portion here is called the power head, and that's where the bulb connects. This is not a replaceable power head. Some valves do have replaceable power heads, this one does not. So again, before we adjust a valve, I keep repeating the same things, but it's so important. Often valves are misdiagnosed because of low load or low airflow over the evaporator coil. So before you start adjusting anything, you have to make sure that you check your superheat. And you check your superheat by using a gauge gauge. This is a very simple gauge. I'm just showing this so that you can kind of see the dial, and you measure the temperature. You equate that to whatever pressure, whatever type of refrigerant you're using. So say if you're using R410A, so if this dial is pointing up near 125 psi, that's going to be right about 41 degrees or so. If it's 410A, the pressure scales on the outside, and then your temperature scales are on the inside. And then you're going to need a good, accurate line temperature thermometer. I like this Cooper-Atkins line temperature thermometer for a very simple device that measures the temperature of the suction line. You compare the evaporator temperature, or otherwise known as the saturated suction temperature, to the actual suction line temperature, and whatever the differential is, and this will be warmer, the suction line will be warmer, that is your superheat. That's a very simple way of doing it. My favorite tools for measuring superheat nowadays are actually more advanced. This is my favorite kit, the JobLinks probe from Fieldpiece. This would be our line temperature clamp, and this would be the pressure transducer that we would use in order to figure out what our saturated suction temperature or evaporator temperature is.
Another quick thing to note is that in built-up systems, this is where adjusting the valves becomes very important, and the most critical thing is that you don't allow flood back to the compressors. And that's why you do not want the valve to be too far open, and when you're in a hot pull down, meaning that when the case is really hot and it's starting to cool down, your superheats will naturally be a little higher. A lot of people think that a TXV sets in a fixed, exact temperature superheat, and that's not true. There is a range of how it operates, and when you have higher load, they're going to run a little higher superheat, and when you have lower load, they're going to operate at a little lower superheat. And that's why generally we say at the outlet of the evaporator coil 6 to 12 degrees, and then back at the compressor more like 20 degrees is what Copeland generally calls for their compressors at least. So we want to make sure at that outlet of the evaporator coil that we have that range kind of built in, so that when you have high load conditions, you're going to be a little on the higher side, and when you have low load conditions, you're not going to drop into that flooding condition. And this is a mistake that a lot of techs make, is they try to dial in their superheat when they're still not fully to temperature in a case, and that results in it going to zero superheat later on once that case cools down. And so again, that's more of a refrigeration thing. Generally in air conditioning, you don't have to touch this. Once again, superheat is a balance of forces that tells us that we have boiling refrigerant in the evaporator coil, and at the end of the evaporator coil, it's fully boiled off and now is a vapor before it goes to that compressor. It's critical that we do not overfeed our evaporator coil, which shows up as low superheat. There are certain applications where you will see superheats lower than 6. You have to have valves that are specially designed for that, and that's where you start to get into electronic expansion valves and things that have a little finer control. There's such a thing as minimum stable superheat, which means that when it starts to get too low, too close to zero, it can become unstable, and you can end up resulting in floodback, which is a very dangerous condition for the compressors. Liquid coming into the compressor crankcases can damage them very quickly, and that's one of the major jobs of the TXV, is feeding that evaporator coil really well, but making sure that we're not going to overfeed and damage it by putting liquid into the compressor crankcase. And on the other side, it helps keep the superheat low enough that it keeps the compressors from overheating. Whenever we're adjusting TXVs, we're thinking in terms of the evaporator superheat first and foremost. And then later on, we move to compressor superheat to make sure that it's not too low or too high. And when we say evaporator superheat, we just mean what is the superheat at the outlet of the evaporator coil. And compressor superheat is what is the superheat at the inlet of the compressor. And they're two very different things, and they vary a lot depending on the size of the equipment. If you have a line set that's crazy long and maybe not well insulated, you could have a huge difference between those two, and there are ranges for both. But on the evaporator superheat, that's where generally between that 6 and 12 range is sort of the sweet spot. Yeah, maybe a little bit more than that, maybe a little bit less depending on the application and the load conditions, but in general that 6 to 12 is where we like to see it.
So first we have to know how to check superheat. Second, we have to actually do it at the outlet of the evaporator coil, not out at the condenser, because we're not looking for compressor superheat here. We're looking to adjust based on evaporator superheat. We have to make sure that it's well insulated and well strapped. Most of these kits come with a really nice brass or copper strap that make it very easy to wrap around the line and firmly attach it to the line. A lot of people want to know where it should attach to the line. They're generally going to give you a guide, and it depends on the diameter of the line where it's attached. So here it's showing you when it's 3/8 to 5/8, it's sort of in that 10 or 2 kind of driving hands position. And if it's larger, 3/4 to 1 1/8, they're suggesting that it goes right on the side. In general, we want to keep it away from the bottom of the line. In some cases, you'll see them attached to the tops even. For smaller equipment, it doesn't make nearly as much of a difference. On this particular valve, it even shows you exactly how much of a change you're going to have based on how many turns, based on turning it full open or full closed. This shows you what the torque rating is on the nut that covers the spindle, And then it's covering how important it is to make sure that the valve stays cool. A maximum of 210 degrees or 110 degrees Celsius is the maximum that you want to get that valve at any point. So protecting it is really important. You can see here that Parker Sportland guide, down the bottom sides, that 8 and 4 position. Again, nobody wants them on the bottom, so that's one thing that you can take into account. And for small equipment, it doesn't make a huge difference where the bulb is, so long as it's properly attached and well insulated. Okay, so now we're going to go ahead and pull off the cap. This is what I happen to have around the shop, so this is kind of a cartoonishly large wrench, so forgive me. I know I'm going to get some criticism for my wrench positioning, but doing this on camera is actually not that easy. There's our stem cap being removed, and there's our spindle. So this is our spindle cap, and this is our spindle. And the right way to adjust this is with a refrigeration wrench. So when we make these adjustments, it's easiest to make the adjustment if we make a mark on the edge of the spindle so that we can see how much it's turned and we can count our turns more easily. It's going to be much easier to do that, especially for making a bunch of very small adjustments. And we have to pay attention to how many turns we've made. So again, a lot of manufacturers recommend only a quarter turn at a time. And so if we make a mark that goes up the stem and that lines up around the edge, now I'll have a really good idea how many turns I've had. Very simply, when I turn it clockwise, that turns the spindle in and compresses the spring. You can see that's about a quarter turn right there. That's going to allow less refrigerant to enter the evaporator coil, which is going to result in higher superheat. If I adjust it the other direction, now that's about a quarter turn the other way. Now that is going to result in lower superheat because I'm allowing more refrigerant into the valve. Again, when I loosen it, so I go lefty-loosey or counterclockwise, that's going to result in less closing force and therefore more refrigerant to flow through the evaporator coil.
Another term that's thrown around a lot with expansion valves are balance port expansion valves, TXVs, TX valves, TEVs, whatever you prefer. Balance port just means that it helps balance that inlet pressure because the force of the refrigerant coming into the inlet of the evaporator coil to the inlet of that valve also affects the valve slightly. So it just distributes that pressure on both sides of the diaphragm instead of just on one side of the diaphragm, allowing it to operate stably under a wider range of condensing temperatures or a wider range of liquid line pressures. So if you imagine you have an application where you have a lot of fluctuation in liquid line pressure, a lot of fluctuation in refrigerant velocity, a balance port valve is going to operate better under a wider range of load conditions. Another term you'll hear occasionally is a hard shutoff TXV or a non-bleed TXV. And all that means is when the system goes off, the valve goes shut, which is a very natural thing to have happen. Valves will go shut when the system goes off unless they have a bleed port because of the balance of those forces. As that evaporator coil warms up, as the pressure in that evaporator coil increases when the system goes off and reaches equilibrium, that closing force increases. Eventually, the evaporator will also warm up, but in the case of a non-running system, a non-dynamic system, the superheat will essentially become zero, which will force the valve closed. So the valve thinks it needs to be closed, and that's what a hard shutoff or non-bleed TXV is, just simply a valve that goes completely shut. Therefore, doesn't allow as much liquid refrigerant to make it back to the compressor crankcase. In general, it's a desirable thing, but in some cases, it can cause compressors to start with a little more difficulty because the compression ratios will be higher when they start up, and that's why a lot of hard shutoff or non-bleed TXVs in single-phase applications in air conditioning require hard start kits or some form of start gear in addition to the run capacitor.
Whenever you are adjusting, again, only in certain applications would you ever do that. You have to allow it to stabilize. Most manufacturers say at least 15 minutes. Keep rechecking your superheat and always make sure throughout this process that you're not accidentally overfeeding, which is getting to zero superheat and slugging that compressor. But first and foremost, make sure that it's installed properly, make sure that there aren't other issues with the system, make sure it's under the correct load conditions, so don't start adjusting the valve significantly while you're still in a hot pull down unless it's overfeeding to the point of flooding. So that would be the only case that you'd want to make any significant adjustments while it's still in a hot pull down. When it's bringing the temperature of a case down or something like that, gets very close to design temperatures, and then you make very small adjustments until you know for a fact that it's stabilized, and then you can continue to make some more adjustments. But always make sure that you flow nitrogen while brazing them in, that you keep them cool, that you use proper line dryers, you do a good evacuation so that way you don't get contaminants inside the body of the valve, which can cause all sorts of issues. Make sure you're measuring superheat accurately and appropriately at the outlet of the evaporator coil, if at all possible. That's where it needs to be measured and adjusted. And then finally, make sure that this bulb is firmly attached in the correct position on the suction line using a proper strap. Brass, copper, stainless steel are the best types of straps because they're conductive, well mounted to the line, and then make sure that it's insulated properly if that's the design of the system.
All right, so that's it. The big facts are, 1, don't adjust a valve unless you know exactly why you're doing it and you're very, very skilled. Secondly, when you adjust a valve, do it very slowly. Generally, you'll hear a quarter turn at a time, which is very slow. On a lot of valves, that will equal a quarter of a degree change. Let it equalize before you make further adjustments. In other words, when you're adjusting a TXV, it's going to be a time-consuming procedure. Another thing is recognize that valves fail for a reason. And so often the reason why a valve fails, it's not just an adjustment thing, has to do with being overheated when it's installed, failing to flow nitrogen while brazing, resulting in cupric oxide or copper oxides being built up in the valve, failure to install or replace line dryers properly, and then finally improper evacuation, resulting in wax and other things that we don't want inside that system, sludge, so on and so forth. Evacuation is a really huge part of making sure that you don't lose valves. Don't overheat the valves. Make sure you use proper line dryer strategies for your application. Make sure that you're flowing nitrogen while brazing. And finally, and most importantly, I think, make sure that you're pulling a really good vacuum. I'll also throw in there just good basic general practices of not leaving lines open, not getting dirt in lines, making sure you're not getting shavings when you're reaming or deburring the copper into the lines. Those are all things that can get stuck in a valve and can cause problems with it. And often those are the causes of improper superheat, not the valve setting itself. That's how and why you adjust a TXV. Thanks for watching.